In this video, we're going to take a look at exam revision for logarithms and exponentials. So what we're doing in this video is just recapping everything we've covered so far for exponentials and logarithms, and we're just going to take a look at some exam style questions based on this as a topic. So other than that, there's not much more to say, so let's just jump straight into the questions. So for the first one here, we're asked to find the exact solutions in their simplest form where appropriate to the following equations. Now for part A here, what I've got is my exponential function of e to the 2x minus 1 is equal to 5. So because I've got my exponential function here, so let's just rewrite this here, or write out again, e to the 2x minus 1 is equal to 5. From here now, because we've got our exponential function, we need to get x here, that's what we're looking to solve for. So in that case, we need to take the natural logarithm here of both sides. And once I take the natural logarithm of my exponential function here, because they're the inverse of each other, they cancel out and I just get left with this power of 2x minus 1. So on the left hand side, like we said, we just get 2x minus 1. On the right hand side here then, we get the natural logarithm of 5. We take the natural logarithm of both sides, so we get ln 5, like so. So we're looking to solve for x here, so what I'm going to do now is add 1 to both sides. So x is equal, 2x is equal here to the natural logarithm of 5 plus 1. And then finally, because we want x here, then I just divide both sides by 2. We get ln 5 plus 1 all over 2 there. Okay, and that gives the exact solution to part A. And then for part B here, what I'm going to do is I'm just going to clear the screen just so it doesn't look like it's getting a bit messy here. So part B then. So what I've got now is 4 lots of the natural logarithm of 2x plus 5 is equal to 1. Now the first thing I'm going to do here is divide through by this 4 in front of the natural logarithm. Okay, and what that would do then is just leave me with the natural logarithm on the left hand side. So ln of 2x plus 5. We've divided by 4 on both sides here, so the 4 disappears on the left hand side. And on the right hand side then it's going to be 1 over 4. Now we're looking to solve for x here, so I want to get rid of this natural logarithm. To do that, we take the exponential function here of both sides. So converting this to exponential form here on the left hand side, in that case, once I take the exponential form here of the natural logarithm, again they just cancel out, they're the inverse of each other. I'm going to get left with 2x plus 5. So we get 2x plus 5 is equal to e, because that's our base here of the natural logarithm, e the power of 1 over 4. Okay, remember 1 over 4 here is my power, that's the same, so it's right up here, e to the 1 over 4, that's the same as the 4th root of e there. Okay, we'll use that at the end, we'll keep it like this for now. So we're solving for x here, so subtract 5 off both sides, so 2x is equal to e to the 1 over 4 minus 5. And then finally, if we just want x here, we need to divide both sides by 2, and that would give us x, so therefore x is equal e to the 1 over 4, which we can write as the 4th root of e. Let's do that here. That's the 4th root of e minus the 5, and then we divide by 2. And there we have it, so that's our solution to part B and the solution to question 1 there. Moving on to question 2 here then. So what I've been given here is 4 ln 64 minus 5 ln 16 is equal to k lots of ln 4. And we're asked to find the value of k. Now this is quite an important skill really, because this is quite useful when we're solving equations that are involving logarithms like this. And what I need to do here now is be able to use the laws of logarithms. So as soon as you see a number in front, we might need to use the rule of powers here for logarithms. And what you also need to be able to spot here is this 4, 16 and 64. So they're all powers of 4. Okay, so that's going to be useful to answer this question. So let's just think about these powers of 4 here. So 4 to the 1 gives me 4. So we can't do much more with that. 16 here, well that would be 4 squared. So 4 squared is 16. And then finally 64 here would be 4 cubed. Okay. So what I'm going to do here is, rather than writing this as say ln 64, I'm going to write that as ln of 4 cubed. So I've got 4 lots of ln of 4 cubed minus 5 lots of ln of 16, so that's the same as 4 squared. So 5 ln 4 squared. And this is all equal to k ln 4. We'll come back to that in a moment once we've got to that point. Now, remember the power rule for logarithms here this power we can bring down in front, okay? That's part of the power rule. So if I've already got this 4 here in front, this coefficient is 4. Once I bring that 3 down in front, we're multiplying those together. So what I'm going to get here is 4 times 3 ln of 4, so that's going to be 12 ln 4. So 12 ln 4. Do the same here now with this part. So I've got 5 as the coefficient here, or minus 5. Take the 2 down in front and times those together, so I'm going to get minus 10 ln of 4. And the reason why we've done that is because notice now they all are the natural logarithm of 4. 12 ln 4 minus 10 ln 4. In that case, we can now simplify. So I've got 12 ln 4 minus 10 ln 4. In that case, we're going to get 2 ln 4, 2 ln 4 there. Okay, and there we have it. So the value of k in that case is simply 2. So for that question, mathematically, there's nothing challenging about that question, but it's being able to recognize what we do and just remembering those laws of logarithms. Okay, so there we have it. So that's our solution to the second question. Moving on to the third question here, and what I've got now is a question dealing with exponential modelling. So Dan has produced an exponential model to measure the temperature, T degrees Celsius, of some coffee cooling in a room T minutes after it was made. So for part A, we're asked to deduce the temperature of the coffee when it's first made. So to answer part A, we need to consider what this value of T must be. So when the coffee is first made, that would be T. So the little t here is equal to 0. It's 0 minutes after it's made. Okay, so we use little t is equal to 0. And all I'm going to do here now is substitute that into our exponential model. So in that case, capital T here is going to be equal to 40e. So that's to the power of minus t over 8. So in that case, that's going to be minus 0 over 8. So minus 0 over 8 plus 25. Okay. So if we simplify this and evaluate, 40e to the minus 0 over 8, well, that's the same as 40e to the power of 0. And anything to the power of 0 is equal to 1. So I do 40 times 1 there, giving me 40 plus 25. So 40 plus 25, giving us 65 there. Okay. And there we have it. So that's our answer to part A. For part B then, we're asked to find the temperature of the coffee after 20 minutes. So in this case, we just set little t here equal to 20. Okay. In that case, that would tell us the temperature of the coffee after 20 minutes. So again, we just use our exponential model here. So capital T here is equal to 40e. So that's going to now be to the power of minus 20 over 8. Power of minus 20 over 8 plus 25. Okay, so plus 25 there. Put this into your calculator here and evaluate this. So I'll just quickly do that. So we've got e to the power of minus, so 20 over 8. Then we times that by 40 and plus 25. So what are we rounding to here? Are we rounding to anything? Nope, just give the temperature. So in that case, if I do it to 1 decimal place, what I get here then is 28.3 degrees Celsius there. Okay, because we're talking about temperature. That's what we're measuring this in. And I've given that to 1 decimal place. So that's to 1 decimal place. Okay, and that's our solution to part B. And then finally for part C here, I'm just going to clear the screen just so we've got enough room to answer this one. So if we just quickly do that. So for part C, we're asked to find to the nearest minute the value of T for which the temperature of the coffee has reached 50 degrees Celsius. So in this case now, what we're looking to do is actually find the value of little t. If capital T is equal to 50, or big T is equal to 50. So in that case, let's go about solving this. So what I'm going to do is I'm just going to write this as the left-hand side rather than the right-hand side. Just put T on the right-hand side. Doesn't really matter. It's just how I prefer to write this. So we've got 40e to minus T over 8 plus 25. Now we're told this is equal to 50 degrees. That's what we're looking to find the value of little t for. So that when this is equal to 50. And what I need to do now is just go about solving this. So first thing I'm going to do is get rid of this positive 25 here by subtracting 25 off both sides. So if we do that, we get 40e to the minus t over 8 there. And that's going to be equal to 50 minus 25, giving me 25. Okay. What I'm going to do now is divide both sides by this 40 here. We want to get rid of this coefficient. So in that case, we're going to get e to the minus t over 8 is equal to 25 over 40. 25 over 40, which we can simplify as 5 over 8. Okay, so 5 over 8 there. And what we need to do now is just solve for t. So because we've got the exponential function here, e to the minus t over 8, I'm going to take the natural logarithm of both sides here. If I take the natural logarithm of this exponential function here, they cancel out, they're the inverse of each other, and I just get left with this power. So minus t over 8, so minus t over 8 is equal to the natural logarithm of 5 over 8. So I'm going to times through by 8 now and then divide by minus 1. So first if we do times through by 8, we get minus t is equal to 8 lots, natural logarithm of 5 over 8, and then finally divide through by the minus 1, and that's going to give me t is equal to minus 8 ln 5 over 8. Okay. Now all we need to do is put this into our calculator. We're asked for the time here, little t, to the nearest minute. So I'll just quickly put this into my calculator here. So I've got ln 5 over 8 and times that by minus 8. And what I get here for t is 3.760029 and so on. So to the nearest minute in that case, this would give me t is equal to 4 there, so 4 minutes. Okay, and there we have it. So that's our solution to part C and question 3 overall. Moving on to question 4 here now, what we're doing is we're solving this equation here. So I've got e to the x minus 5e to the minus x is all equal to 4. Now I think this can look quite tricky because we've got this power here of minus x, so e to the minus x. So let's just write this out as e to the x minus, so rather than writing this as 5e to the minus x, this is the same as 5 over e to the x, okay? And this is all equal to 4. And the reason I've done this is because I think it makes it a little bit clearer what we need to do now. Whenever we're solving equations, generally fractions are a bad thing. We don't really like those being involved. So what I'm going to do is get rid of that fraction. And the way I'm going to do that is to multiply through by this denominator. So I'm going to multiply each term here by e to the x. So if you've got e to the x and you times it by e to the x, so e to the x times e to the x here, well, basic rule of indices would state that we add the powers here. They've got the same base, so in that case we get e to the x plus x, giving me e to the 2x. So we get e to the 2x here, so e to the 2x. If I've got minus 5 over e to the x and I times it by e to the x, they just cancel and I just get left with minus 5. And then this 4 here, well, that would simply be 4e to the x. Okay. Now, hopefully, you might spot what I'm going to get here is a disguised quadratic. So what I'm going to do is I'm going to set this equal to 0. I think it makes it very clear then. So e to the 2x minus 4e to the x minus 5 is all equal to 0. And then, like I said, hopefully you do recognize this now as a disguised quadratic. What I'm going to do now is set u here as e to the x. In that case then, e to the 2x, well, I could write that as e to the x squared. So in that case, that's the same as u squared. So this e to the 2x we're writing as u squared minus 4e to the x, that's the same as minus 4u. If we're using this substitution here, and then minus 5 is all equal to 0. So from here now, we just need to solve this quadratic here. Generally what you'll find is these type of quadratics do factorize rather than making you solve using, say, completing the square or the quadratic formula. And in this case, this does indeed factorize. So if I write this out here with a u at the front of each bracket, then what I'm going to get here is two numbers that have a product of minus 5 but add to give me minus 4. In this case, I can have minus 5 and plus 1 there. Let's just double check that. U squared plus u minus the 5u giving me the minus 4u, and then minus 5 times 1 is giving me minus 5. Perfect. So from here then, what I need to do now is say that u, I'll just solve these individually, so u minus 5 is equal to 0. In that case, we're saying u is equal to 5. Or we have this solution here of u is equal to minus 1. Okay. Now u equals 5 here doesn't mean much because we have this substitution. So what we're actually saying here then is e to the x is equal to 5, or e to the x is equal to minus 1. Now there's a bit of an issue here with one of these solutions, so take a moment now to see if you can spot which one has the problem, and hopefully you recognize that the problem here lies with e to the x being equal to minus 1. I can't actually solve this, and the reason for that is because there is no value of x such that I get -1 here, okay? The reason for that is because if you take the natural logarithm here of both sides, we get x equal to the natural logarithm of -1, but if you put that into your calculator, you would get an error. That isn't a mistake, that's just what would happen here. So in that case, we omit this solution, okay? This wouldn't give us an actual solution. My only solution here lies from the fact that e to the x equal to 5. So, if I just change my pen colour here just to make this clear. So, e to the x is equal to 5. So we're just solving for x now. In that case, take the natural logarithm of both sides here, giving me x is equal the natural logarithm of 5. Okay, and now that's our solution there to that question. Moving on to the final question here, and what I've got now is this function f, which is given below. So what I'm going to do is just go back to my original pen colour here, and let's have a go at solving this question. Now for part A, we have to show that the inverse function here is equal to e to the x minus 1 plus 4 all over 6. So how would we do this here? Well, let's start with our original function, f of x. So if I just write this out here, I think it makes it a little bit easier to see. So f of x is equal to the natural logarithm of 6x minus 4 plus 1 there. So we're just finding the inverse function here to start with. Now, finding the inverse of a function shouldn't be too challenging, but it might be tricky here when we're working with logarithms like this. Okay, so the first thing we do is we change this to be y equals the natural logarithm of 6x minus 4 plus 1. And what I'm going to do now is I'm going to rearrange and make x the subject. So the first thing I'm going to do here is get rid of this plus 1. I'm going to get the natural logarithm of 6x minus 4 is equal to y minus 1. From here now we want to get rid of the natural logarithm. So we're going from logarithmic form to exponential form. So in that case, once we take the exponential form here, they cancel, they're the inverse of each other. So I get left with the bracket of 6x minus 4. And that's going to be equal to e to the y minus 1. Okay. Remember, we use e here because we're working with the natural logarithm. So the base of the natural logarithm is e. So from here now, I'm just going to solve for x. So add 4 to both sides. So 6x is equal to e the y minus 1 plus 4. And notice now this is taking shape here. They had e to the x minus 1 plus 4 over 6. At this point here, we've got 6x is equal to e to the y minus 1 plus 4. So we're pretty much there. All I'm going to do now is divide by this coefficient of x here, this 6. So x is equal to e to the y minus 1 plus 4 all over 6. Okay. So from here now, all we need to do to finish with is just write this as inverse function notation. So f inverse like this. So f inverse of x, and obviously we just change this y here to be an x. So the inverse of f of x here is given as e to the x minus 1 plus 4 all over 6 as required there. Okay. And there how it starts our solution to part A. Hopefully that wasn't too challenging. And the good thing about this question is, even if you couldn't do part A, you could still attempt part B, okay? Because we were given the inverse function like this. If we weren't given the inverse function, we might have struggled a little bit, but in this case, we can still attempt part B because we have the inverse function here. So for part B, we have to solve the equation of the inverse of f of x being equal to 7 over 6. And we're asked to give the solution in exact form here. So where do we begin? Well, let's just take our inverse function. So that's e to the x minus 1 plus 4 is all over 6. Now this is equal to 7 over 6. So this is equal to 7 over 6. So the first thing I'm going to do here is get rid of this denominator of 6. So to do that, we multiply both sides by 6. I'm going to get e to the x minus 1 plus 4 is equal to 6 lots 7 over 6. The 6 are going to cancel here, and I'm going to get left with 7. I get e to the x minus 1 plus 4 is equal to 7. And from here now we're just looking to find the value of x. So I'm going to get rid of this plus 4 here. To do that we subtract 4 off both sides. So we get e to the x minus 1 is equal to 7 minus 4, giving me 3. And because we've got the exponential function here, I'm now going to take the natural logarithm of both sides of my equation. So once I take the natural logarithm here of this exponential function, again, they're the inverse of each other. I feel like I said that quite a lot, but obviously they will cancel out and I get left with the power here. So I get x minus 1 is equal to the natural logarithm of 3. And then finally, we just want x here, then we just add 1 to both sides. So x is equal to 1 plus ln of 3 there, okay? And there we have it, that's our solution in exact form. Remember, when it says exact form, it just means keep it in terms of natural logarithms like this. Don't write anything in the decimal. But there we have it, so that's our solution to part B, and that gives us the solution to that question overall. And that brings us to the end of this video on exam revision for logarithms and exponentials. And that brings us to the end of our revision for Year 1 pure material. In the next video, we're going to start by introducing the applied module.